Right, here comes our second video on gravity, and we're dealing with the concept of G, the gravitational field strength. I'll get the terminology right on this one, gravitational field strength. Now this is not to be confused with big G. Okay, I'll show you how they link in a minute. But this is little g, in other words, and you're familiar with what this is, 9.81 meters per second squared, or people often say approximately 10 meters per second squared. The rate at which objects fall to the Earth, the speed, the acceleration at which objects fall to the Earth with, but also as well, approximately 10 newtons per kilogram, the force that each kilogram will feel on Earth. Okay, let's try and see how we can derive that from big G here. We know that the force, according to Newton's law, is gmm over r squared. Those two m's are different, hence capitalised and small case, lowercase, sorry. And we've said that this is a force per unit mass. So therefore, if we divide the force by mass, we get g, or the acceleration, because this is the weight divided by the mass. So therefore, if I divide that by mass, they merely cancel out, and I get g m over r squared, minus, just to be pedantic, but more often than not, they'll just be looking for a magnitude. Good, so that leaves us with g is going to be gm over r squared, and not only can we work out what g is on Earth, but you can also work out what g is on different planets, as long as you know their masses and their radii. So let's try g on Earth and see whether it comes out to be in the order of 9.81. This gives us 6.67 times 10 to the minus 11. I suggest you learn that constant rather than digging around on the data sheet. 6 times 10 to the 24, which is the mass of the Earth, and the radius of the Earth, 6.4 times 10 to the 6, or 64,000 kilometres. Don't forget to square that, often forgot. And that gives you 9.77 metres per second squared, or indeed newtons per kilogram, whichever you prefer. Probably best to imply newtons per kilogram, because that infers the logic which you started with here. Okay, not identical to 9.81, but then again, densities vary as you go through the Earth's. It's slightly squashed. It's not a perfect sphere, centripetal accelerations, etc., etc., but we're in the right order of magnitude. Let's, why don't we check what's going on the Moon as well? Let's give you the radius of the Moon, which is the radius of the Earth divided by 3.7, and the mass of the Moon is the mass of the Earth divided by 81. If you want to, just to write them out explicitly, I will just plug it into the calculator to give us, okay, 1.7 times 10 to the 6, and 6, and 7.4 times 10 to the 22 meters and kilograms. So therefore, G on the Moon would be gm over r squared, 6.67, 10 to the minus 11, memorize it, by 7.4 times 10 to the 22, divided by 1.7, 10 to the 6, remember to square it, often forgotten. I'll just plug that in. It should be about 1.2, but just get the actual value. XP6. Yeah, 1.7 it says here, newtons per kilogram. So significantly different to that on the Earth, nearly a tenth. Okay then, what about Jupiter? Should we see what Jupiter is? The radius of Jupiter is 11.2, the radius of Earth, and the mass of Jupiter is 320 masses of the Earth. So therefore, well, I'll just bolt it straight into the equation this time. G is going to be gm over r squared, obviously Jupiter and Jupiter. That gives us 6.67, 10 to the minus 11 by 6 times 10 to the 24, that being the Earth, 320, divided by 6.4 times 10 to the 6, 11.2 lots of that, all squared. And that gives us, just plug in into the calculator. Sorry about noise. 11.2 all squared, 24.9 newtons per kilogram. Yep, and they sound about right. So G on Jupiter, G on the moon, and of course G on Earth. Good, so that's how you use the equation. It's probably worth saying at this stage that G on Earth, we suggest it's the same. So if here is the surface of the Earth, and we say that things across the whole of Earth fall with G or experience G, the number of newtons per kilogram. A quick question will be, how far do you have to move beyond the surface of the Earth in order for G to change by 10%? So if here we were at 0.9 G, how far from the surface of the Earth do you have to go in order for G to change by that quantity? If you think you know, hit pause, and otherwise here comes the answer. So we obviously know that this is all taking place from the centre of the Earth, not drawn to scale, but we want to know 0.9 of G. So let's get the equation. G is going to be gm over r squared, but we're looking for 0.9 of that. What's the radius, not of the Earth, but of the distance from the centre of the Earth in order to get 0.9's worth? So let's do some rearranging. Gm over 0.9 of G, and r is going to be therefore the square root of that. Okay, let's plug in the values. 667 10 to the minus 11 by 6 times 10 to the 24 over 0.9 by 9.81 square rooted gives us a value of 6.73 times 10 to the 6 meters. Okay, that's from the centre of the Earth, so therefore the distance from the surface is going to be that minus the radius of the Earth, 6.4 times 10 to the 6 meters, which gives us 330 times 10 to the 3 meters, or 330 kilometers, and that's huge. So really, we can assume that 10 from the surface of the Earth is fairly straightforward. It's the same for all activities which humans do on Earth. It's going to be the same. Right, let's start drawing the function and seeing what's happening here. Let's imagine we have G in the centre of an object. Let's say Earth. And here is r, the radius from the centre. Then remember, though G is measured from the surface of the Earth, it is at the surface in which G will be the largest value, 9.81 newtons per kilogram, let me write. Let's do this in meters. So this is at 6.4 times 10 to the 6 of them. Beyond there, it behaves as an inverse square law, so it falls off inversely squared proportional to r. That was a mouthful, that didn't really make sense. So it's dropping off quite rapidly. Inside the Earth, interestingly, it does increase linearly. Now, the mathematics of that is quite tough, but if you imagine, if you're at this point, say, inside, it's we're going to say that the let me just draw a dotted sphere here. Everything outside is going to cancel, and it's that which is inside that's contributing to the gravitational field you might feel at that point. And very quickly, we did this in the last video, that you can re-express the mass as a density times volume, which is 4 over 3 pi r cubed over r squared, and they cancel out to give you g rho 4 over 3 pi r. So actually g is directly proportional to the radius of the planet. Hence, when we went to Jupiter, it was 24, even though you're much further away from the centre at the surface. However, what's happening is it's incorporating much more mass. Okay, so inside it is linear. Mathematics, you can look into yourself to work out these spheres, whether they cancel out. And outside, it drops as 1 over r squared. Good. So what does that suggest then? Well, so that's how we graph it. Very close to, let's deal with these very close to distances. We can say, so like the surface of the Earth, we can say that G is uniform. And so here is a uniform gravitational field. Right, what does a field mean? This is the first time we've come into this concept field. A field is the force per unit, in this case, mass. In the case of electricity, it would be the force per unit charge. So, I suppose in films they talk about force fields. Bear that in mind. Fields indicate the direction of the force. So in a uniform field, all of that would be towards the centre of the Earth and straight down. It's nice and uniform. However, what happens beyond in this region here? Well, in that region there, if you have a uniform field, spherical field, so now we go spherical. What happens is, I've drawn this quite badly, let's make that a little sharper. The field lines are pointing towards the centre of that object. So we start to get a spherical field, or if you like, radial field. They're pointing towards the centre of the object. And very, very close up, I suppose, if we're looking at this, that is magnified to being a uniform field. But that's quite important. So bear in mind a few points here. One is force field. Field indicates the force exerted on the mass, because it's a gravitational force. Near the surface of the Earth, you get a uniform field, which means they're all straight and in line, the same direction on every object. As we move further out, you start to get a radial field, or a spherical field, which means they're pointing towards the centre. And I suppose the big idea, though I glanced over it quickly, was it's the force per unit mass. I glanced over that, but that's quite critical there. In other words, forces are exerted between two objects. Let's say the Earth and the Moon. And you can't have a force without there being two objects. But what G is showing is what would happen if you had a 1 kilogram object there. What force would it experience? And therefore, if you had a 2 kilogram mass, then you just merely multiply what it experiences by 2. If you had 100, you multiply it by 100. But it's referencing one object to another object. So you can have field lines around one object because they would indicate what the force would be if you placed a unit mass at that point. So it's subtle, but it's quite interesting, that idea. Okay, let's move on with a few more problems for us. Let's take a look at now the Earth and the Moon and look at their field lines when we have two objects together, because we've only done the field lines out of one object, but when you have two. Okay, let's just indicate first of all the surfaces as opposed to their centres. And also, I think it's important to think to yourself, like a physicist, what is going to happen? So let's imagine we put an object here, our 1 kilogram there. We know we're going to feel a force from the Earth, and we know we're going to feel a force from the Moon. However, I would argue that the force from the Moon is going to be smaller than the force from the Earth. force of the Earth will be larger than the force from the Moon. Because we know the Moon is smaller, it has less mass. So therefore, it's probably worthwhile when you're thinking about a problem like this by designating a positive direction to the force. And if it's therefore pointing this way, it will be positive. If it's pointing that way, it will be negative. Okay, so everything before here, I would argue, would be pulling back, would be negative. Because it's all going to be under the line. And then it will drop off. There will be a point where the competing forces are the same. And so therefore we must go to G as 0. Badly drawn there. And then, of course, it's going to be pulled in this direction where that's the dominant force. So therefore, we're going to then start to get the Moon taking over. So there is G between two objects. Obviously, one is a bigger mass than the other. The Earth is a bigger mass than the Moon, and we've defined that to be positive. So therefore, the Earth is below the line, the Moon is above the line. If I told you that, if the separation was equal to r, and this is at 0.9 r, could we work out the mass of the Moon knowing the mass of the Earth? So the mass of the Earth is 6 times 10 to the 24. Knowing that this is the point at which the forces are equal, can we suggest work out the mass of the Moon? If you think you know how, hit pause, otherwise here comes the answer. Okay, if the forces are equal, then you know that G's must be equal as well. Because it just depends on the object you multiply it by to work out the actual size of the force. So the G's must be the same. So therefore we have Gm over r squared of the Earth gives us Gm of the Moon over r squared. Now, bearing in mind, of course, 0.9 is from the Earth. So I should say this is 0.9. I've drawn that badly. 0.9. And of course, from here to here is only 0.1. Because these equate, I can knock those out, G, so therefore that leaves me with mass of the Earth by 0.1 r squared divided by 0.9 r squared gives me the mass of the Moon. And of course the r's drop out, because they're the same as well. So in effect, we have the mass of the Earth by 0.1 squared over 0.9 squared, giving us 0.1 squared over 0.9 squared is as good as saying 1 over 9 squared. So that's the mass of the Earth over 81, which is exactly what we had in the first instance here. Okay, good. What do we need to then think about? What would it look like, therefore, the field lines coming out of these objects? Bearing in mind, of course, that the Earth is experiencing... Let me redraw it so it's a bit neater. Earth and Moon. Well, the field lines always point towards the centre. It's agreed. But then there comes a point where they start competing with each other at about 0.9. So really what we have is we have the field lines looking like competing magnetic field lines, if you need to draw an analogy. With, of course, this being their separation and that being the 0 point. So later on, we'll be drawing how equipotentials and field lines compare. So it's a good idea to think about how field lines look on a surface, and therefore equipotentials from those. Just wondering whether we have another example. No, I think that's it. Brilliant. Hope that makes sense.